When a containerized application works perfectly in isolation but feels invisible to the outside world, the missing piece is usually networking, because networking is how that application becomes reachable, useful, and testable. Containers can make networking feel strange at first, since a program inside a container may think it has its own network identity, yet it still depends on the host to connect to anything beyond that small world. Beginners often expect that if an application listens on a port inside a container, it should automatically be reachable from the host or the rest of the network. But containers deliberately put a boundary in the middle. That boundary is not there to be annoying, and it is there to give you control over exposure, segmentation, and security. In this episode, we build an exam-level mental model for container networking, focusing on port mapping, common network types, and the trade-offs between privileged and unprivileged container operation. Once you can explain who can reach what and why, container networking stops feeling like magic and starts feeling like policy. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. A helpful place to begin is with the simple idea that networking is an address and path problem, not just a port problem. A container can have its own Internet Protocol, IP, view, its own interface names, and its own routing table view, but those are created by the runtime and exist within the host's broader networking reality. The host still has the physical network connection, the real addresses on that connection, and the responsibility to decide which traffic is allowed in and out. This is why container networking is often described as virtual networking, because the container's network view is an engineered environment rather than a directly attached physical cable. For beginners, the most important mindset shift is that a container is not directly on the network by default in the same way the host is. It is closer to a process in a managed bubble that can talk out, and sometimes can be talked to, depending on the chosen network design. If you keep asking yourself where the boundary is and who is translating traffic across it, you will understand most container networking scenarios without memorizing details. Port mapping is the first concept that turns a private container service into a reachable service, and it is often the concept learners encounter before they truly understand why it is needed. A port is a numbered doorway on a host that allows multiple services to share one IP address, and when an application listens on a port inside a container, it is listening inside the container's network namespace, not automatically on the host's interface. Port mapping is the runtime's way of creating a controlled bridge between a port on the host side and a port on the container side, so traffic arriving at the host can be forwarded into the container. The key idea is that port mapping is an explicit exposure decision, because it states which container port will be reachable, from where, and through which host port. Beginners sometimes think port mapping is just a convenience setting, but it is more accurate to treat it as part of your security posture. If you do not map a port, the service may still run, but it will be reachable only within the container's own network context, which can be exactly what you want for internal-only components. Port mapping also connects directly to the idea of network address translation, NAT, because many common container network modes rely on address translation to let containers communicate outward while keeping their internal addresses separate. NAT is a technique where traffic is rewritten as it passes through a boundary, allowing private addresses to share a public address for outbound connectivity. In a typical container arrangement, containers may receive private IP addresses on an internal bridge network, and when they reach out to the wider network, the host rewrites the traffic so it appears to come from the host's address. This allows many containers to share the host's external identity, which is efficient and convenient. The trade-off is that inbound reachability becomes controlled, because outside systems cannot simply address the container directly without the host performing a translation or mapping. That is exactly why port mapping matters, because it defines the inbound translation path from a host port to a container port. When you understand port mapping as controlled inbound translation, the behavior becomes predictable instead of surprising. It also helps to understand that there are multiple network types because no single network design fits every container use case. Some containers should be easily reachable from the outside, like a web service, while others should never be reachable directly, like an internal worker process that only consumes messages. Some workloads benefit from isolation so that one container cannot easily see or interfere with another, while other workloads need simple, fast communication between containers. Network types are the runtime's way of giving you those different patterns without making you build them from scratch. At exam level, you can think of network types as templates for how connectivity is arranged, including how containers are addressed, whether they share an address space, and how traffic is forwarded. The big idea is that choosing a network type is choosing a connectivity and exposure model. If you picture networks as different rooms with different doors and rules, you will naturally start asking which rooms should connect and which should stay separate. A common network type in container environments is a bridge-style network, where containers connect to a virtual switch on the host. In this model, containers typically receive private addresses on that bridge, and the host routes or translates traffic between the bridge and the outside network. This feels similar to how home routers create a private network for devices while using NAT to share a single public address. And that analogy helps beginners understand why containers can reach out while still being separated. In a bridge model, containers can often talk to each other on the bridge, which can be convenient, but it also means you must consider whether that container-to-container visibility is appropriate. Bridge networking also makes port mapping a primary mechanism for exposing services, because the containers are not directly attached to the host's external interface. That default separation is often a security benefit, because it prevents accidental exposure, but it requires intentional configuration to make services reachable. For exam reasoning, bridge networks are the classic middle ground between isolation and usability. Another network type conceptually is host networking, where the container shares the host's network stack instead of having a separate network namespace. In this mode, the boundary between the container and host is thinner, because the container's processes see the same network interfaces and address bindings as the host. The immediate advantage is simplicity and performance, because there is no translation layer and no need for port mapping in the same way, since the service can bind directly on the host's network. The trade-off is reduced isolation, because the container no longer has a private network identity, and it can potentially interfere with or observe aspects of the host's networking more easily. This can increase risk, especially if the containerized application is not fully trusted, because network isolation is part of limiting blast radius. Host networking can also create port conflicts, since the container and host are now competing for the same port space. For beginners, the safe takeaway is that host networking can be useful for specific cases, but it is not the default because it trades away a major part of container isolation. A third broad idea is that containers can be attached to isolated networks that are designed for internal communication, where containers can talk to each other but are not directly reachable from the outside. This pattern is useful when you want a multi-container application where one part is public-facing and other parts are internal, such as a front-end service talking to a back-end service. In such a design, only the front-end needs external exposure, while back-end components can remain hidden behind the internal network boundary. The beginner mistake is to map every port for every container, which can accidentally expose internal services that were never meant to be public. The more mature approach is to expose only what must be exposed and keep the rest on internal networks that limit reachability. This is a security mindset as much as it is a networking design, because reducing exposure reduces attack surface. At exam level, knowing that network types can represent internal-only segments helps you interpret scenarios where services should communicate with each other but not be visible to outside clients. Name resolution is another layer that shows up in container networking, and while it can be implemented in different ways, the concept is stable. Inside a container network, containers need a way to find each other by name or address, and some container platforms provide internal domain name system, DNS, behavior, so that container names can resolve to container addresses on that network. For beginners, the important point is not the specific mechanism, but the idea that networking is not only about packets, it is also about how services locate each other. If container A needs to call container B, there must be a stable way to identify B, and hard-coding IP addresses tends to be fragile because containers can be recreated with new addresses. This is where internal naming becomes useful, because it provides a more stable identifier than an ephemeral address. When internal naming fails, the symptoms can look like the application is broken, but the root cause can be simple. The containers cannot resolve each other's identities. If you remember that name resolution is part of the network story, you will be less likely to chase the wrong problem. Port mapping also deserves a deeper security-oriented explanation because it is easy to treat it as a purely technical step and miss its implications. When you map a container port to a host port, you are deciding that traffic reaching the host on that port should be forwarded to a specific container process. That means any security controls that apply to inbound traffic on the host, such as firewall policy, now matter directly to the container service. It also means that if the host is reachable from untrusted networks, the container service becomes reachable too, unless additional protections exist. Beginners sometimes think of a container as inherently safer because it is isolated, but isolation does not help if you expose a vulnerable service directly to the internet. The container boundary can limit what an attacker can do after compromise, but it does not prevent compromise if the service is exposed and weak. Port mapping is therefore a place where secure defaults matter, because mapping only what is necessary reduces the number of entry points. On the exam, if you see wording about limiting exposure, the right mental move is to think about which ports are mapped and why. Now we can address privileged versus unprivileged trade-offs, which are at the heart of whether container networking is safe or risky. Privileged operation, in container terms, generally means the container is granted broad capabilities and access that more closely resemble what the host itself can do. Unprivileged operation means the container runs with a reduced set of capabilities and with stronger boundaries, limiting what the containerized process can change or control. This matters for networking because many networking operations, such as creating interfaces, changing routes, or manipulating firewall rules, are sensitive operations that can affect the host or other containers. If a container has too much privilege, it may be able to alter network behavior in ways that break isolation or create security exposure. If a container has too little privilege, it might not be able to perform certain legitimate functions, such as binding to low-numbered ports or performing specific network diagnostics. The trade-off is therefore between operational flexibility and reduced blast radius. For beginners, the safest default is to prefer unprivileged containers and grant additional privileges only when you can justify them clearly. A common misunderstanding is to assume that privileged containers are needed for good performance or for normal network connectivity, when in reality, most application containers do not need elevated privileges to communicate over the network. Most services only need to open a socket and send or receive data, which does not require special capabilities beyond what a normal user process can do. Privileged mode tends to be relevant when the container is acting more like infrastructure, such as performing network control functions, monitoring, or running workloads that need deeper interaction with host devices. The danger is that giving a container broad privileges can weaken the very reason you chose containers, which is controlled isolation. If the container can access host networking features too directly, it can potentially sniff traffic, reconfigure interfaces, or interfere with other workloads, depending on the host's security posture. This is why you should treat privileges as a scarce resource, not a convenience setting. At exam level, the rule of thumb is that higher privilege can solve some functional problems, but increases risk, so it should be granted intentionally and narrowly. Unprivileged containers, especially those that avoid running as the all-powerful user inside the container, support a more defensible model where compromise has fewer consequences. Even if a service inside a container is exploited, the attacker's process may be limited in its ability to change network configuration, access host interfaces, or pivot to other containers. This is not perfect isolation, and it still depends on correct host hardening, but it is a meaningful risk reduction. In networking terms, unprivileged containers are more likely to be constrained to their assigned network namespace and to the ports and mappings provided by the runtime. They rely on the runtime and the host firewall to define exposure rather than being able to define exposure themselves. This aligns with the general security principle of centralized policy enforcement, where the host sets boundaries and workloads operate within them. For beginners, a useful way to remember the value is that unprivileged containers make networking behavior more predictable because fewer actors have the authority to change it. Predictability is both a security and troubleshooting advantage because fewer hidden changes can occur. There is also an important connection between these privilege choices and the concept of least privilege in networking exposure. A container that only needs to serve HTTP traffic should not have the ability to manipulate the host's firewall or create new network interfaces. Similarly, a container that should only be reachable internally should not be launched in a way that allows it to bind directly to the host's external interfaces. These are design decisions, and they show up in practice as network type selection, port mapping selection, and privilege selection. Beginners sometimes treat these as separate knobs, but they are really parts of one policy, defining who can talk to whom and who can change that rule set. If you choose a bridge network and map only the required port, you are expressing a narrow exposure intent. If you choose host networking and run a privileged container, you are expressing a broad exposure and control intent, whether you meant to or not. The exam often tests whether you understand that these choices compound each other, creating either a tighter or looser security posture. Keeping the compound effect in mind helps you pick safer answers. A final exam-level insight is that many container networking problems are actually misunderstandings of boundaries rather than failures of technology. A service might be listening inside the container, but without port mapping, no external client can reach it. Two containers might be running fine, but if they are on separate networks, they cannot see each other without an intentional connection path. A container might have the right environment variables, but name resolution inside the container network might not match the host's view, leading to unexpected connection failures. A container might behave differently under host networking because it now shares the host's ports and interfaces, causing conflicts that did not exist on an isolated bridge. Privilege changes can also alter what the container is allowed to do, which can make a network diagnostic tool work in one mode and fail in another. When you learn to interpret symptoms as boundary and policy mismatches, you stop blaming the application first and start checking whether the network model actually matches the desired connectivity. That is the kind of reasoning Linux Plus is aiming to measure because it shows you understand the architecture rather than just the vocabulary. To close, container networking is best understood as a set of deliberate choices about reachability, segmentation, and authority. Port mapping is the explicit bridge that exposes a container service through the host, often using NAT concepts to translate inbound traffic from a host port to a container port. Network types define the connectivity model, such as a bridge-style isolated network, a host-shared network stack, or internal-only networks that keep backend components hidden while allowing service-to-service communication. Privileged versus unprivileged operation defines how much authority the containerized process has over networking features, and that choice directly affects both security risk and operational flexibility. When you combine these ideas, you can reason clearly about why a container is not reachable, why two containers cannot communicate, or why a configuration increases exposure beyond what you intended. The safest habit is to expose only what must be exposed, keep internal traffic on internal networks, and grant only the privileges required for the workload's purpose. If you can explain these trade-offs in plain language, you have the container networking foundation needed for both exam scenarios and real-world container environments.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.